Introduction. So I'm really happy to be able to give a talk here. It's an interesting series that I followed several of them. So I will talk today about the usefulness of iSheet model intercomparisons. So if you ask whether they are useful, you have already answered the question. So the main idea behind it is those two paragraphs that are coming from IPCC reports, AR4 and AR5, that dynamical processes are not well understood and definitely not well included in iSheet models. That was back in 2007, but even in 2013, there was still a lack of potential quantification of potential instabilities or rapid grounding line retreat and the magnitude of Antarctic iSheet contribution in the future. As an iSheet modeler, you get a certain impression, and that was my immediate impression, that you have a lot of people that say that iSheet models need improvements on the one hand, and that we only have a very few amount of people that actually work on improvement of those iSheet models, working with those iSheet models and developing those iSheet models. Another impression is, and that is more recently, is that many papers that work on observations, they write in their conclusions or even in the abstract that, and yet this newly discovered process has not been included in iSheet models. Yeah, it's a bit difficult if you just observe it to have it already included. The fact is that the improvement of iSheet models is very incremental, and it's very slow compared to the amount of observations and the wealth of observations that we currently have, and also the understanding of the processes behind it. But I think that iSheet model intercomparisons, or ISMIPs, may contribute to the incremental improvement of such iSheet models. There is another way of representing this by a popular mean. Popular, it's maybe not popular anymore because it's over. The ship is free. But this is a way of also thinking about this, or how I see it. Now, what are the objectives of iSheet model intercomparisons? First of all, it's to test and compare existing numerical iSheet, iShelf, glacier models, but more specifically under similar conditions that allow a comparison between them. And there are different sets of comparisons that can be done. You have those that are mostly focused on verification. It's typically an idealized geometry, and a verification means that you also have some analytical solutions under idealized cases to which you can compare and verify a numerical solution. Or you have then a validation in which you more go to a real case and see how good your model can reproduce what is currently observed. What those two verification and validations can lead to is to narrow down uncertainties, but also to detect errors in model codes. And all that together enables you to come to a model improvement. Now, I'm going to show here a very, very, very brief history of model intercomparisons. These are not all the model intercomparisons. These are the ones that either I participated in, or that I led, or that I did without participating, but I did the experiments. There are a number of others in which I did not participate, nor where I did not do the experiments. So it starts with the ISMINT series that I will briefly introduce, and then we have ISMIP series and then the MISMIP series, and then we come to ISMIP 6. So the later ISMIP 6 ones are more real case experiments. All the former ones are idealized cases. So I will start off with the idealized cases. So ISMINT goes back to 1996. It was launched in the early 90s. So that's quite recent, but iSheet modeling in itself is a rather recent subject if we compare that to climate modeling or ocean modeling. It is that these models, they saw the light in the early 90s, but if you want to do an intercomparison, you need a couple of them in order to make comparison possible. And this was a very simple, basic experiment, but very interesting. It looked at an ice sheet on a flat bed with then a prescribed surface mass balance and temperature. That's typically if you want to do intercomparisons, but also a prescribed grid size that was rather coarse, because at that time computational facilities did not allow you to run so many things as you can do now. Now you can run this experiment easily on a smartphone. But also it had the temperature calculation, but without a coupling. And verification was possible for the flow line case using the 2D steady state Navier-Stokes solution. Overall, these models are in agreement. It allowed also to detect some errors in different models, but there were some differences that were noted, especially when you compare it to analytical solutions, as is shown in this figure. And these were really, by the way, how you numerically represent the ice thickness evolution equation. Now, this is a particular problem in ice sheet modeling. In general, it's because these equations are stiff equations, and they are numerically a bit harder to solve. So you need to take some extra care to solve such equations in their transient evolution. And that is why we were dealing even at the end of the 90s, still with problems like this, how to get an ice sheet evolved on a flat bed. Another of these set of experiments, because there were several of them, was the thermomechanically coupled case. So in this case, not only temperature was calculated, but it also influences through the Arrhenius relationship the rheology of the ice. And that was a same series, same set of experiments, similar geometry. It had a slightly higher resolution of 25 kilometers. But if you look at all these model results, there was a far larger spread across the models for all the variables. The amount of melt that it produced, melted or not melted, the size of the ice sheets, the velocity of these ice sheets, and also the appearance of cold spokes, as is shown in this figure, which was heavily discussed. What was the origin of these cold spokes? It could be a physical process, as we see here in this figure of the Hill-Shaw cell. During one of the conferences, I don't know if people are around here that were at the ISMINT conference in workshop in Grindelwald in the, I think, end of in 1998. Where Andrew Fowler asked for 2 glass plates and a bottle of ketchup to show this experiment that if you put ketchup between 2 plates and you remove the plates, then you get this patterning, as is shown in this figure. Such patterning of cold spokes gives you areas where you have fast flow and then slow flow alternating. So it can lead to self-organization. You have this fingering, typically also what you observe at the Cycle coast. But there were some questions of whether how highly was this related to numerical problems, like for instance, growing a circular ice sheet on a square grid, or the numerical symmetry breaking. And this numerical symmetry breaking was very well seen in, oh, I go too fast here. Yeah. Oh, there was a slide that disappeared. Yeah, sorry. Yeah, it was in another experiment, ISMIP HEINO, that was done to explain Heinrich events. And that experiment showed, a lot of symmetry breaking and a lot of different responses of different models, which were probably numeric. And so Richard Hindmarsh, among others, looked at this more carefully and looked what is the importance of membrane stresses in this whole thing, because all those models initially were shallow ice approximation models. It's also related, this instability and the appearance of these spokes, on the transition between cold and temperate ice. And a recent paper of Christian and Eliza Mantelli show how what the effect is, and that you must have a zone of sliding possible under sub-freezing temperatures. And that allows you to also stabilize some of these effects. So that's basically a discussion that is still ongoing, while we always think that the thermomechanical coupling is a solved case. There was another experiment in that ISMINT, and that is on ice shelves. There were only 4 models in there. It was led by Doug McHale. And it was applied to a geometry of the Ross Ice Shelf. And as this figure shows here to the right, it was quite well represented. I mean, this is just the dynamic response. So it's only the velocity field for a fixed geometry, and everyone working with the same geometry. But you see that the velocity field in all those models was pretty well similarly, except maybe at the borders, well represented. There exists an idealized case experiment for the ice shelf equation that was launched by Vincent Romelard, but yeah, this is unpublished. This has never gone any further, but the experiment exists, and yeah, I've tested all my ice shelf equations using that setup. It's very interesting to do so, to test an ice shelf model. Now, in the model development, it became more and more clear that the shallow ice approximation was not something that we could use for long, and that for certain problems, and especially problems at the ice stream onsets, grounding line areas, ice shelves included, that you needed to have membrane stresses included. And so the first full Stokes models saw the light, but also some approximations, like my own approximation. But then also, yeah, nowadays you also have other approximations that go a step further, that make it calculate even quicker. But you also have the shallow shelf approximation. And so this brought us to the idea, well, let's test those models. What is the validity? How well do these approximations compare to a full Stokes model for a problem where you normally should need a full Stokes model? And so this was also an experiment without kinematics. So we have a fixed geometry on which we calculate the velocity field. And this was done for a bumpy bed, a sinusoidal bed, in 2 dimensions, with ice on top of it, with a surface slope to drive the motion. And then the experiment was done for different aspect ratios. So that means you have large, wide bumps, or you have very narrow bumps. And for that setup, the shallow ice approximation always gives exactly the same result, because it's independent of that aspect ratio. Now, higher order models, they react on this. So if you take a very large aspect ratio, so then we have a large velocity change across these bumps, and this difference becomes smaller and smaller. And you see the full Stokes, which are the top color here, and the non-full Stokes, which is this other color. I think it's green, I'm not sure. And then you see that they follow nicely, except for the very high aspect ratio, very low aspect ratio. I mean, this means very high aspect ratio, so very small length scale. Then you see that the full Stokes models show a much better representation than what you get from those approximations. So you can see what is the limit of these approximations. In that, we also had a verification experiment in which we allowed also the ice sheet to evolve and to a steady state, and that over a Gaussian bump, ice flow over a Gaussian bump on a sloping bed. So it's a prognostic run, and therefore we have an analytical solution for the steady state. And this was also rather well represented by both the full-Stokes and the shallow and the approximation models that use membrane stresses. So that was very neat to see that, yeah, to have a confidence in those approximations and what they could do. This was also an experiment in which, for the first time, the spatial resolution was set free, so everyone could choose their own spatial resolution, which is normally the resolution is a function of the problem you solve. So the users or the experimenters, they were asked to use a resolution in which they thought the problem was solved. So it was not a setup. Just as an anecdote, I showed the experiments for a given resolution, and so that people could compare to see that they were in the right range, and everyone used that. Then afterwards, I submitted results with a much higher resolution to be sure. But you showed that this to show that resolution is something that is really embedded in people's mind and that they just copy whatever is available. So that brings us now to another set of idealized experiments that are focused on the grounding lines, because yeah, the grounding line problem is a problem that is outstanding for a long time. And even though we know that membrane stresses do play a major role in that, it was not sufficient. So even in ISMINT, there was already a first intercomparison of ice sheet models with grounding lines. It was for flow line models. And that was also the first intercomparison I joined in. But yeah, all these models, they behaved very differently. So here you see the initial steady state under initial conditions that were the same for each of these models. So you see grounding line positions varying widely. And then also when you force the model either by a drop in sea level and then go back to the initial state, try to get back to the initial state, or you do a change in surface accumulation, well, you get an advance of a grounding line, but most models, they don't retreat anymore. And the problem was there with resolution, because here the resolution was way too coarse. That was later shown in this paper by Andreas Wili and Tony Payne, the importance of spatial resolution in having ice sheet grounding lines advance and retreat properly. But it was not until that we had a clear theoretical understanding of stability of grounding lines that we could really test it against some known solutions. And so the MISMIP was an analysis of grounding line equilibria based on the paper by Christian Schuve in 2007 that shows the, as a function of the bed profile, the different equilibria of the grounding line that you can have. And there was also another part in it that basically you have for an unbuttressed, so this is the flow line case, a flow line ice sheet, that you have unique grounding line positions. So that means that all these previous experiments that made an advance, but if you set to the initial conditions your model back, that it just stays there, these are completely wrong. So this was then the experiment. You grow the ice sheets to multiple steady states in which the ice gets stiffer, and then you make it softer again. And basically the grounding line positions should advance and retreat and just take the same position in. So if you apply that to the same thing here to several models, well, this is the advance and retreat in one way, but here we see the retreat. Then you see the retreat is basically a wide variety. This was with a given resolution. This was with a higher resolution. So you see that resolution does matter, but resolution is not everything. It's also the physics that are behind it. And it's clear that if the same experiment was done for this over deepened bed, in which you have areas where hysteresis occurs, meaning that you have different positions of grounding lines for the same conditions, depending on where you're coming from, either advancing or retreating. It's clear that shallow ice models were not capable of doing anything with that. So you needed membrane stresses and also sufficient high spatial resolution to cover this. So here we see some examples of shallow shelf approximation models of different with different numerical implementations. So it's you can basically also classify this, and that was a first way of classifying models in terms of this experiment. So I made here a very simple classification, 1, 2, and 3, meaning that these are models, large-scale ice sheet models that use a very coarse resolution, but basically they use at least a shallow shelf approximation. So they have they do have the membrane stresses. The 2 is same type of models, but with a significantly higher resolution. So a resolution that is spatial resolution inferior to 1 kilometer. And then the third type is like, yeah, let's say best of both worlds. It's where that's number 3 here. That is where the parameterization of the Schoof equation is used to guide the grounding line position, which allows the model to use a coarse grid, but obtain the same grounding line positions as theory predicts. So this may be a bit uncertain in how this works in the real case, but at least it gives you, in a theoretical framework, a way that grounding lines can advance and retreat. The second step was to put this into 3 dimensions, knowing that buttressing also plays a role. Yeah, ice shelves are not everywhere unbuttressed in the Antarctic ice sheet. They have a back stress that they exert on the grounding line. And so this was an experiment to reproduce curved grounding lines. So starting from a very a case in which is completely unbuttressed, and then make a grounding line advance to create a curved grounding line. It's very subtle as an experiment, but it was meant to check the transient behavior and see how models cope with that transient behavior. And quite intriguing is that you can make a difference between the different physics used by the models. So here I select a series of models that are that represent or that use the highest resolution. And then you see that you can clearly make a difference between how a full Stokes model, that is the line here, behaves compared to a hybrid model, an L1LX or an SSA model. So you have some differences. And also here in yellow are these models that use this parameterization of the flux. So you see some quite different types of response that is also seen here. So it's a very good agreement between the full Stokes and this L1LX model in the response. But this was only done, as I said, for models that have either the sufficient high resolution or that use this heuristic. But if you apply that on, for instance, at that time, a number of projections that were made on loss of ice in Pine Island Glacier here to 2050, and that was done during the sea rise experiments, and that was done by several other people, by Ian Yoken, Lionel Favier, and Hélène Seroussi as well. Then you see that the spread of sea rise, which is this whole bunch of spread that you see here, and then the ones that do resolve this grounding line and use models at sufficient high resolution as is prescribed here, then you see that this narrows down the uncertainty. Of course, it also narrows down the numbers of ice loss. Well, together with that, you also have theoretical developments, and that is also still ongoing. So not only are there observations, there are theoretical developments, which are very interesting and intriguing. I have two examples because I'm not exhaustive on this, by Sam Pegler and also by Marianne Hasselhoff, in which people are looking more closely to the effect of buttressing on ice sheets. And basically also these developments are gradually also taken into account in our understanding, to which we can maybe use some of these expressions or derived expressions to improve our understanding of numerical ice sheet models. One of the experiments that was done was, for instance, by Hilmar Gudmundsson, in which you take a narrow channel similar to a geometry of Pine Island Glacier with an overdeepening and a grounding line that that is situated here in this overdeepened part. And the fact that you have sufficient buttressing in your narrow trough, buttressing by the ice shelf, as can be seen here, then you can obtain stable grounding lines. And this was well, first of all, an experiment in which only two models were used, UA and Elmer Ice, a full Stokes model and an SSA. And you see that they both are capable of producing such a thing. And this led then quasi-automatically to a new model intercomparison called MISMIP Plus, in which two factors were considered. First of all, can models reproduce these stable grounding lines on these unstable slopes? And also, how do they react when you apply an ocean forcing on it? Here, the ocean forcing was taken as something realistic, but parameterized. You see the equation below. And so here you see the geometry. So you have here the area of the overdeepening, and the unstable slope is between this dot and that neck here. And so the initial steady state that needs to be produced is on that unstable slope, and then you force with melting, the grounding line retreats, and from there you either stop the melting and then the grounding line should advance and get stable again, or you continue to melt and you continue to retreat. So it means that the buttressing is sufficiently important to, in absence of forcing, to create a new steady state. So that shows that buttressing is very important in suppressing marine ice sheet instability. So here you see the results. And also this experiment compared different sliding laws. So we see here the loss of ice by the melting, the continued loss of ice by the melting, but here the stabilization due to the stopping the forcing. It's also more sensitive for Coulomb sliding laws compared to Weertman sliding laws. So they lose more quicker ice, but they also gain a new equilibrium. So all these experiments were done with models at a high resolution, so definitely 1 to 2 kilometers. I did the experiment, and it's clear that the experiment, because of the relatively high amount of sliding, and definitely much more sliding compared to the MISMIP 3D experiment, that it is a bit less sensitive to spatial resolution. It doesn't mean it's not sensitive. So that brings us to real-world cases. And real-world cases are a bit more complicated in the sense that there are many more things that differentiate and controls ice sheet models. For instance, if you apply or do an intercomparison on the real world, you have less control than for idealized experiments. And the response that you get is influenced by many things. That was already a case for idealized cases, but it's even more so. So first of all, spatial resolution that we have seen before, but we have numerical methods that we have seen before. But it's also then the physics complexity, because in general, you let all the modelers use their model the way as they want to use it. You also have different representations of physics, for instance, the degree of parameterizations. But also you need to initialize a model. Most of the time, in these idealized cases, you start from a steady state because that is easy to work with. Yeah, here you need an initialization, either a steady state or a transient situation. And there are different methods to do so. It can be spin-up, it can be data assimilation, and as we will see, that makes a major difference. But there is also the evolution of thermodynamics, depending also on the timescales you consider. There are the different boundary conditions, what you use as a sliding law, what other fancy things are included in your model. What is the data that you use? The basic data, like for instance, bed topography. There are different topographies that exist. You have BedMap2, but then there is also BedMachine that also recently became available for Antarctica. That's also a data set that is continuously evolving when new data is appearing. So that makes comparisons a bit more complicated. And then the last one is the forcing, and I put it in italics to show that basically the forcing is not the most, well, it's normally considered as the thing that is applied, the same thing that is applied for everyone. So that is not exactly model dependent, but it can become model dependent if some parameters are produced by the model. Like for instance, the model that uses a PDD model to produce melt instead of using melt that is provided by the forcing. So I have here a number of, and again, it's not a full list. I just took a few, so sorry if your model is not in there. This was just to show again the different categories of models and the resolution that is used in those models for a series of ISMIP 6 experiments that have been done. What their numerics are, what the physics is, and then especially also their initialization. So you have initialization based on data assimilation, that's DA, or SP is spin-up, or EQ is an equilibrium. And then yes or no inclusion of thermodynamics and thermomechanical coupling. But so we have high resolution models, we have lower resolution models with some kind of treatment of the grounding line, and then we have a series with the parameterizations at the grounding line. So that is more or less the groups we have. So one experiment that is a bit between real case and an idealized case, because it's on a real ice sheet, but it's a completely irrealistic experiment. That's the fun of it. That's the fun of ice sheet modeling, basically, because you can play God in the sense that you can do anything with an ice sheet without doing any harm to the real world. But so this was, well, to see what is the effect of buttressing, or more precisely, what is the effect of debuttressing. So what happens if we remove all the ice shelves and keep them removed? And so the reaction of your ice sheet should then be, if you have rapid changes, they should be due to marine ice sheet instability, because there is no buttressing available. It can be slowed down by bedrock topography, especially when you reach again a slope upwards, but even a pinning point can slow down, but maybe not completely eradicate or stop the marine ice sheet instability. So this was run for 500 years. You see the response of the different models. It's a quite large spread between 1 meter and 10 meters in 500 years sea level contribution for these models. Most of the models, they do lose ice in the West Antarctic ice sheet. We see here the standard deviation. So the lighter the color means that the more the models agree. Some models, and that's here the darker color, they lose ice also in East Antarctica. Some of them in certain scenarios also around the Totten Glacier catchment. And those lead then to very high sea level estimates. But in total, this enabled us to revise the figure of what is the mass loss due to marine ice sheet instability. There was an estimate given by Bamber et al. Several years ago by looking at yeah, where if we put the grounding line at the the stable bed slope, how much ice do we lose? Well, this is in a more dynamic environment, multi-model intercomparison, and that leads us to 2 to 5 meters in 500 years. Yeah, most of these losses are not yet in steady state. So here we see an overview. In general, yeah, as I said, wise loss in most models, and these type 2, the response may be influenced by initialization and the temperature evolution. One thing that was, we tried to understand whether this was due to, yeah, what were the factors that were influencing this large spread. One of the factors, it's not the sole factor, is the sliding or friction law. So the more plastic you're sliding, the faster your ice loss. And this was already seen in the MISMIP Plus, and that was already shown in other models. So that's not new, but it means that for really plastic models like Coulomb friction, that you can get major contributions to ice loss. This is also shown in this, but this is only one model, and so it's very difficult to compare different models with only then one Coulomb friction law. This is the result of one model using several friction laws, but yeah, that gives you the same result as what is here generally seen. Right, so go to the real cases then. Again, that started already in ISMINT, these first intercomparisons on what the Antarctic ice sheet should do. In a greenhouse warming experiment that was quite schematic and relatively simple, and we see here how the volume changes. And so all these models, not only do they start with different volume changes of the present day Antarctic ice sheet, most of them as a result of the spin-up, they also gain mass, except for one, which was the Grenoble model, and that was especially around the Saipel coast area. Again, these models were at a very coarse resolution, and that was before we understood a bit better how grounding lines worked. Another experiment that followed, another ensemble or another intercomparison, was sea rise. That was for AR. That was for AR5, eh? Yeah. Am I right? So that had a realistic forcing for the climate, but a kind of bulk subshelf melting. So it means you melt the ice shelf for all the ice shelves for a given number that increased. And so you see a very large spread in response. There are also models in there that clearly lack grounding line dynamics, and yeah, that do show changes. So the spread and uncertainty here was quite large. Yeah, I wanted to put this slide in for LARMIP, and I wasn't finished yet. So yeah, just LARMIP exists. But okay, just continue with ISMIP 6, INITMIP. So that's on initialization of the Greenland and Antarctic ice sheet, and I show you an example of Heiko's paper on the initialization of Greenland. So where we see how these models, or the modeled response, or the present day reconstruction of the ice sheet largely depends on the initialization method. So you have data assimilation in those type 2 and 3 models that is relatively closer to what is currently observed, and you have a wider spread. But also another aspect here is the model drift. I mean, what happens if you have no forcing and you let your model run for a certain amount of time? So that was also quite important in not only Greenland, but also in the Antarctic modeling. But if we then look at the results of the Antarctic modeling, yeah, the goal of this experiment is completely different than the goal of, and that was the same for sea rise, than the goal of the other idealized case, ISMIPs. This is to get probabilistic ice sheet projections according to different climate change scenarios. in which, models are initialized and then models are forced by climate models, in which some interaction is provided to link ocean forcing to ice sheets. So in general, this gives you a large uncertainty, which is due to the fact that you have quite a lot of models participating, but also models with different physics, models using also different boundary conditions. But there is an extra uncertainty that is added here, is because they are forced with several CMIP 5 and CMIP 6 models. And just to give you just a flavor of this, this is well, it's slightly different experiments, but it's two completely different forcing models. But you see that to the left, there is no differentiation that you can make between an RCP 2.6 and an RCP 8.5, which is possible in other models. So this is largely due to the forcing and not really to the model itself. But there are some critical model factors or model independent factors on the subshelf processes. It's the way you link ocean forcing to ice shelves and so on. And there are several ways of doing this and several sensitivities related to that. And then also spatial resolution, again, controls the grounding line retreat and potential instabilities, especially due to resolved or not resolved bedrock irregularities. So my concluding remarks, ISMIPs, they have a positive effect on the development of models. So first of all, we have seen they can detect errors, they make numerical improvements, especially for such stiff equations. We can test, engage the parameter and model uncertainty. We can do sensitivity testing and also detect leading order physics. So what is important and what is not important if we want to simulate, for instance, marine ice sheets. And it also gives you a way of sorting models in a way, not saying per se, this model is bad, this model is good, this one passes not, but I mean, what needs to be done or what needs to be taken care of. But the development of ice sheet models and also the design of such intercomparisons is rather slow, because you start from observations, you start understanding those observations, you go to theory, and then you have to implement that in ice sheet models, and then it requires also testing. So also what increases uncertainty is that you have more and more ice sheet models, and also models that are easily available, that are public domain, that you can that have good manuals and that are relatively easy to use, but there are quite some inherent difficulties in modeling in itself. And then one of the pitfalls that it's probably a pitfall that I fell in. It's if models pass a test, are they then verified? In many of these grounding line experiments, the high resolution is required, but you can do a test on a very high resolution with your model, but then apply it to an Antarctica with a low resolution. Well, it doesn't mean that you have passed the test. If you pass the test on that same resolution, then I think it's acceptable. But changing resolution is very important. So it's very critical in the behavior of models. But despite all this, many uncertainties still remain. Basal sliding, subshelf melt processes, calving, damage, hydrofracture. There's also the cliff collapse. As this figure here shows, how projections of different studies show at the year 2300, a big gap in response if marine ice cliff instability is included here in one model compared to other models. But there is also, the understanding of ice shelf buttressing and debuttressing, rapid GIA forcing, and as I mentioned before, the initialization. So my last slide is just to leave it there. There are still major outstanding questions that remain for an ice sheet modeling community. For instance, is marine ice sheet instability already underway for certain West Antarctic glaciers? Do we need a cliff instability to project future sea level rise? And for what forcing and when can we expect ice shelf collapse? These are questions that I think if we are able to respond to those in the next couple of years, we are capable of reducing a part of the uncertainty. So with that, thank you very much for listening, and I'm happy to take any questions.
Thank you very much, Frank. Do we have any questions from the audience? Matthew's clapping. Just give it a moment. Sometimes, often people take a while.
Yeah, Bill has a question.
Oh yeah, okay.
That's
Bill,
not
please.
clapping. It's not tilted.
Hey Frank, enjoyed your talk, and I would second what you said about these intercomparisons being really useful for model development and validation. My question was, at the end, you showed a slide about Mickey, marine ice cliff instability. And we've been in the situation for several years where one model produces projections that largely depend on Mickey, and most other models don't have Mickey or don't turn on Mickey. And I'm wondering if you have any ideas for comparisons that might move us forward in understanding of how Mickey works, how realistic it is, and whether it depends on model numerics.
Yeah, it's a very neat question. I do have an opinion on this, which may not be shared by the whole community. I think we require a bit of theoretical considerations because, I mean, I'm not questioning whether Mickey exists or not. I'm questioning how you go from observations directly to a parameterization, which, yeah, it's, if you don't know the process, that's what you normally do. But normally in a model world, you apply a parameterization for things that are not that sensitive, that you don't want to investigate further, and that you just need that parameterization to solve the problem. If that problem becomes then really dominant in your response, then it becomes more critical on what is the validity of such a parameterization. So I think some theoretical work is necessary. On the other hand, there is also the forcing that does play a role, because in order to have cliff instability initiated, you need to have a ice shelf that is collapsed, because you need to have a cliff that exists there. Now, yeah, the question is, I think we can put the ball in the camp of ice shelf dynamics, try to understand how ice shelf collapse, because if an ice shelf is still sufficiently buttressing and is not collapsing, you will not have a cliff, and then your Mickey will not start. You need to have that cliff before it starts. So I think that is one thing that's why I have here this third question for what forcing and when can you expect ice shelf collapse, because that is in a way a predictor of potential onset of Mickey. So, but as I would like to reiterate, yeah, it's not that I'm against it, but I think some more theoretical work is needed that allows you then to, yeah, look at, can we analyze the stability of such a system mathematically, and see, yeah, how models or how parameterizations cope with it. I do know that several groups are working more precisely on not only theory, but also on modeling Mickey. So we will see some advances in the near future there, and that is really needed.
Yeah, thank you very much. Maybe you could recommend some good speakers for ice shelf modelers specifically. I believe Roger is on the call. Do we have any questions from anyone? Second question. There's a message in the chat from Heiko. She says, very nice overview.
Thank you, Heiko. So it either seems that I was very clear or I was extremely boring.
We have a question from Olga.
Olga, good.
Olga, would you like to unmute perhaps?
I think I'm in a bit noisy environment, but anyway, yeah, Frank, thanks for the talk. So what do you do if the theory that you're relying heavily on turns out to be wrong?
Yeah, I didn't capture that, but I'm looking for the.
It's in the
She says, what do you do if the theory that that you're using turns out to be wrong?
Yeah. Well, look further. So what do you mean that the Schoof theory is wrong?
Yep.
Yeah. I know that you say that. Yeah. Yeah. No. There's one way that we can different ways to look at it. So even if it's wrong. You can always see whether it behaves, how it behaves compared to models that don't need that theory to do it, that can solve the problem completely.
No, I guess my question was more about your design of experiments.
Yeah, I should have said a bit more about it. It's very important and very critical to design experiments. And some of these experiments, I think, were not very well designed, but was hard to design them differently at that time. Because you also have to make sure that you have sufficient potential participating models in there that can cope with that. So I think that like MISMIP 3D was maybe not the most ideal case to work on. But I think I can criticize any of those setups of idealized cases that we took. But I would be more than happy if you would suggest something that could be tested with numerical models.
Absolutely, because your idea of having idealized configurations with extremely smooth bed, and especially one on a flat bed, it doesn't tell you much whatsoever.
That's true.
So in that regard, just even ISMINT with bumps was much more revealing than whatever it is in MISMIP with a like inclined plane. I mean, if you want to see a dependence on the bed slope, you have just one constant bed slope, right? So you cannot see anything happening.
Yeah.
And again, such things could be easily kind of deducted even from Christian's paper 2007 and GGR. Just read it carefully.
Yeah. Good. But you're more than welcome to contribute to designs of further tests. There is one thing that, well, given the uncertainties where we are looking at is to think, for instance, on a another intercomparison that would focus more on calving and damage. If someone has ideas on what we should investigate and how we should investigate that.
Marianne wrote a paper on that, and there are at least 3 suggestions how to do that.
Okay, good.
So just read papers, it's already there, Frank.
Yeah. Thank you very much. Thank you very much, Olga. Yeah.
Thanks for the talk.
Thanks, Olga. Oh, we have a question in the chat from Vivian. How would you determine which of the large number of models gives a more realistic representation of actual ice dynamic processes?
So wait, I'm going to try to find the chat. Oh, yeah, okay, I have it here. Yeah, that's, yeah. Yeah, in such an intercomparison, you don't want to, in the first place, you want to have a sufficient wide community and you don't want to make everyone angry. So it's very, what is a realistic representation of ice dynamics? I think that the basic ice dynamics we have captured in these ice sheet models. As a general, the evolution of ice sheet, ice shelf system for a given forcing that we understand. I think what is now getting more and more crucial is more some details, like for instance, yeah, how an ice shelf melts, where that is really important. But the way it evolves, the way it will respond to that forcing, that I think we have captured. But then also how an ice shelf breaks up. If you look at the Larsen B breakup in the early 2000s by yeah, major hydrofracturing, I don't think we can reproduce such a thing with a given forcing right now with ice sheet models, such a breakup. So that these are now more specific, those processes that allow you to capture that, and it must be captured in a more statistical way, because you cannot just predict when the next iceberg breaks off with an ice sheet model or an ice shelf model. But you can predict what the long term or the longer term or decadal time scales calving front position is. So meaning what is the mean calving rate and by what is it influenced. So yeah, there is a variety. Calving, I think, is still something that is not well represented in models in general. And the way how ice shelves fragilize and the damage on ice shelves, it's the same thing. And Heiko has a very good answer. Would say that often the modeler's decisions are equally or more important than the model itself. Yeah, this is also what I said on the use of the resolution of your model. It's a choice that you put in there, but that's a choice that's very crucial.
So there's a very large parameter space and important decisions to make
there is a large parameter space, but okay, from a series of sensitivity experiments that are done, and that so some are more important. Yeah, you can have the lead order effects in there, also depending on time scales. I think the paper of Kevin Bulthuis showed the what are the important parameters in the response functions. Yeah, it's clearly everything that was related to the rheology of the ice shelf and the amount of melting. That's leading order compared to other things that are related to, for instance, sliding. But sliding may become more important whenever you have a loss of ice shelves and things like this.
I'm just a bit conscious of the time. We have a question from Ronja.
Ronja,
would you like to unmute, Ronja? Oh, sorry.
Yeah, well, for next MIP, the idea would be centered on ice shelves and like, for instance, calving and damage. Because that is something that is, and that is quite crucial. But at this moment, I will take the recommendations of Olga with me, something that we need to look in. But I think that is basically a bit the next step. But yeah, everyone is free to organize a MIP. The thing is that none of these MIPs that I have shown, at least none of the idealized case MIPs, had any funding. So they were all done by the free basis in the free time of the community. And the fact that you have so many people that are involved in that and doing those experiments and put time in there shows that it is for everyone a quite important business to do so.
Do we have any perhaps final questions from anyone? Now everyone is asking. Veronica, would you like to unmute? I think it's nice to get other people talking.
Thank you, Frank, for the very nice talk. I was wondering, do we know to what degree uncertainties of input observations such as bed machine influence the different models? Like, is there a different sensitivity to different models?
Yeah, the way to answer that is, let's say to use different data sets with one model under the same conditions and then test that. And you can do the same thing with another model. Right now, the uncertainties related to that are embedded within the major uncertainty. But maybe that Mathieu has some, did some experiments on that and has some experience. I think it's also quite related to the spatial resolution that you use.
Yeah, I don't know if I should answer that question. I don't know if we have enough bed topography maps available to actually, we can try to quantify what is bed machine versus bed map 2 in terms of models. And I think there would be quite a good agreement in terms of where the models go, because in bed map 2, many of these troughs were missing. So that will impact all models, I think, in the same way if they do capture these troughs. But now, certainly bed machine is full of problems in many places. So when we run these ISMIP 6 experiments, for example, it's hard to tell whether the models are wrong because of the initial states, the bed topography, the forcings. It's very difficult to disentangle the different uncertainties. So I'm not really answering the question, but
no, but it's true, and it leads sometimes to different results if you use a new data set or even an update. Even an update of bed machine is sufficient to get different areas, timings where grounding lines change a bit and so on, even if you're using the same resolution.
Okay, thanks.
Thank you very much, Veronica. Are there any other final questions?
It's lunchtime in New York, no?
Yeah, everyone's perhaps dying to go for lunch. Okay, thank you very much, Frank. Thanks again.
Thank you for the invitation.
For speaking. It's a wonderful contribution to the series. Yeah, thanks again. And I hope everyone has a great rest of the day. And we'll see you all next week.
Thanks, Frank. Okay. Great talk.
Thank you.
As always.
Bye.
Cheers. Goodbye.